Welcome to the session on simple cases in fluid flow as part of the NPTEL MOOC on transport phenomena and materials. In this session, we will be taking up a problem in spherical coordinate system. So, the problem we are taking up is flow around a sphere. Now, in a spherical coordinate system, even simple problems tend to be quite tedious because of the algebra involved. So, you may pause this lecture time to time, work out some of these steps so that it will be clear at the end how we went about these derivations. So, we will take up the problem of flow around a sphere, and once the solution of the velocity components are available, we will derive what are called the drag terms, namely the force acting on the sphere because of the velocity gradients, and then we will see how we can arrive at the Stokes law, which is very important in metallurgical industrial problems, where terminal velocity of particles is used in extractive metallurgy problems. So, this is the strategy that we are adopting for this problem. So, we are actually going to start off with a problem statement as we normally do in most of the transport phenomena problems, and then we will be writing the boundary conditions, but here we make a deviation from the other problems we have done in previous sessions. We will be writing the boundary conditions using the stream function. So, this is because the solution will be accessible if we use the stream function for this particular problem. And then we will write the governing equation also in stream function form, which we have looked at already in an earlier session, and the analytical solution will be sought, and once the solution is available as a stream function, then we can again get back the velocity components because we have the definition of stream function already available with us. So, here is the problem. The problem is basically there is a solid sphere which is smooth and rigid, and the liquid is flowing around that. So, the direction of the liquid flow is shown vertically upwards, and you may want to call the velocity vector as u, which is in the upward direction. So, what this problem will render is that the spherical symmetry is now lost because the intersection between the spherical symmetry and the vertical velocity will be cylindrical. So, we will actually use a spherical coordinate system, but for an axisymmetric case. Okay. So, that is what makes the problem a little tedious with respect to the algebra, and we will see how best we can come about this limitation. Now, for the domain has to be defined. So, as we have discussed in an earlier session about the domains, the domain in our case will be the entire space around the sphere, which means that in terms of the r radius, if you take the radius of the sphere to be r, then the r, small r above capital R, that is anything that is above the sphere is a part of our domain, and theta is of course varying in the complete range, that is 0 to pi, which means that theta is going in this way, okay, and r is going in that way. So, the entire range of theta is a part of our domain. Now, the boundaries are actually defined at two locations. The first is quite straightforward, it is on the surface of the sphere. And then we have also a boundary condition available at far field, that is far enough from the sphere, which is basically in the limit of the radius tending towards infinity. And the problem we are going to look at is in the regime of fluid flow, where the Reynolds number is very small. So, this is also referred to as a creeping flow. So, that is the liquid is going to follow the curve of the entire sphere very closely, and does not actually separate out. So, that makes the problem a little easier to handle and will give us a analytical solution in the end. So, here is the concept map of how this derivation is done. So, each of these boxes contain some aspect that was discussed either earlier or will be discussed as part of this lecture. So, this is how we go about. We have already seen the general form of the Navier-Stokes equation, and we can actually make a special form for the specific case of the Newtonian fluid, incompressible fluid, and in a coordinate system that we are interested, etc. So, we do have special forms of Navier-Stokes equation available, and we already have seen what is the continuity equation, that is the mass conservation, and using the continuity equation and the idea that when you have two velocity components, you can perhaps create a function that will capture these two into a single unknown variable. So, stream function for example. So, that idea is also going to be used, and we can realize that the Laplacian operator is different in different coordinate systems. So, you do then see that for the coordinate system that you choose, operators are different, and combining with the axisymmetry that we have, then we see that some of the terms of the del square operator will be different, and therefore, we create the E square operator. And we see that this problem is actually for an external flow around a sphere, and we make the velocity to be unidirectional and the domain to be around a sphere, and the regime to be applicable for creeping flow, and then we put all these things together to arrive at the governing equation, which is called the Stokes equation, and then we seek the analytical solution. So, this is how we go about. So, here we take up one at a time, and one thing that we take up is generally highlighted in the yellow background. So, we take up the stream function first, the definition that will be refreshed for us to use at this moment. So, the axisymmetry is being imposed, which actually implies that the phi component of the velocity is not there. So, there is nothing happening in that direction, and which means that you can reduce the continuity equation to only 2 terms. And whenever there are equations of 2 terms, then you could use that as a constraint to create a function which actually will satisfy this equation and also give you the components of the velocity. So, that is a function that we are referring to. So, that is a stream function psi. Okay. So, according to then this equation, you could see what kind of a function would satisfy. So, there is a sin theta there. So, we watch out, and we have already seen which component of the velocity should be the positive and negative. So, this is actually from a convention that we have already seen earlier. So, this is the definition that we have, and we are going to use this. So, we write our equations in psi, but we always look up this component definition whenever we want to translate from psi to Vr and V theta and vice versa. Okay, so, I would leave it as a homework to check that when you substitute these 2 velocity components into the continuity equation, then the equation would satisfy. Okay, so, now we look at the boundary conditions. So, the boundary conditions are to be written as follows. So, the solid sphere is impenetrable and it is smooth with the no slip condition on top. So, which means that the velocity components are 0. Okay. So, the Vr, that is the radial velocity on the surface. So, this means that on the surface of the sphere. Okay. So, that is 0, and similarly the theta component also will be 0, and this is basically the no slip condition and impenetrable wall condition. And if you look at the definition, then this, when you inspect, then it should also imply a condition on psi, and that condition, as you can see, that if Vr were to 0 at r is going to capital R, that means dou psi by dou theta also should be 0 at the same condition. So, this is one boundary condition we get from the first condition, and using this definition, for example, you could then combine here, and then we will get the boundary condition with respect to the r and theta. Okay. So, you do have these 2 coming up, and which means that we now seek, so our problem will become seek psi in a form that satisfies these things. Okay. So, we must have a psi which will actually obey this kind of a form, so that it makes sense for our problem. Okay. So, we can then go further and see what we can also look at as a boundary condition far away. So, by far away we say that it is basically it implies basically when r tends to infinity, and of course, applicable for all thetas. Okay. So, again we look at the definition and look at what kind of a boundary conditions are coming out. So, if you see Vr definition and combine with this, then you would get the condition that would be coming up here. Okay. So, how did we write the Vr as u cos theta? You could actually see that the theta is varying in this manner. Okay. And we are actually looking at the vertical velocity, and which means that at this point theta is 0. So, velocity is u, that will be coming up matching here, and at below it should be minus u. So, cos of pi is minus 1, and that will be matching. At this position the velocity is 0 in the vertical direction, which also will come as u cos pi by 2 is 0. So, you could see that just by simply taking a component we are able to write the Vr which is far away, okay. And this will be actually all 0 on the surface, but at these respective theta positions far away, this is how the velocities are written. So, similarly you could also see how theta has been used. Theta is used so that you could actually combine with the boundary condition, and then we would arrive at the far field condition for psi. So, we now have two sets of condition on psi. The differentials when r is going to the capital R on the surface of the sphere, and when r goes to infinity, that is far away from the sphere. So, we have got 4 conditions on psi. So, these are 4 are listed here, and then we can see that when we combine these 4, that is 1. So, you have got 1, 2, 3 and 4. So, when we combine these, then we can suspect what kind of a form of the psi could satisfy. So, you could see that perhaps we can actually look at a form of this nature, so that when we take a derivative with respect to theta, then you still have r square, and then when r goes, you can actually see that it would actually give you the satisfaction. So, you have this functional form that will be reasonable, and we want to then see what is the generalized form that would actually solve the equation. And so, you could actually seek that perhaps it should be a function of r, and then see what kind of functions will satisfy. Okay. So, because this is only at r is equal to, this is far field, okay, but this we see at any r. So, what kind of a function f of r is suitable such that at far field it will give you this kind of a value. So, that is the solution that we are now requiring. Okay. So, what we normally do in all the integration and differentiations that we do in engineering problems is that whenever we want to propose a solution, then we insert that solution into the differential equation that should be satisfied, and then see what form of the function will be reasonable. Okay. So, that is what we are going to do here also. So, here we have then come up to the usage of the stream function. So, we now move on to introduce the E square operator, and the E square operator is basically in place of nabla square or del square operator. That is, reason is basically because we are actually using the axisymmetric case. So, directly by looking up the del square operator, Laplacian operator for spherical coordinate system would not help, because we have already constrained it to be axisymmetric. So, some terms would drop out, and therefore, this is the operator we are going to use. So, which means that the equation will have to be then looked at. Now, so this is done and this is done, and when we see the Navier-Stokes equation, we have already seen that you have got the terms that would have the Reynolds number with the diffusive term, and here you have got the transient and the advective terms, and we have got the pressure drop term, and then we have got the body force term. Okay. So, which means that in the limit RE tends to 0, then you could see that when RE is taken to the left hand side and right hand side on the numerator, then you would see that only the diffusion term will survive. So, we will see that we can actually take a special form of the Navier-Stokes equation, which is also called as the Stokes equation, and use that as a governing equation for us. So, the form of that is here. Okay. So, this we have already introduced in an earlier session. So, this is basically its equivalent, okay, equivalent in the rectangular system would be, for example, dou square u is equal to 0. Okay. So, that is the equivalent, but we already have used the stream function. So, when you use that, it would then give you a fourth power, and then this is how the equation is looking. And we have already seen that the E fourth is nothing but E square acting on itself. So, it is actually nothing but the E square operator coming twice, and that itself we are actually already seeing what is the form. So, we have seen the form here E square. Okay. Now, the functional form we are proposing the solution to be is here. So, what we see is that when we insert it into the governing equation, it should satisfy. So, here we are asking what form of f of r would satisfy this equation. So, that is what we are asking basically. Okay. So, once we have it, then we have the solution available. Okay. So, what we do is that we now go ahead and substitute the form that we have and see if we can simplify. The reason being that the form we have chosen is already separated in terms of the variables. So, f of r and sine square theta are separate. So, therefore, we could actually see if some simplification is possible. So, what we do is that we substitute and act the operator on this function, and then we will see that if you look at how this part is acting on here, because if you see dou square by dou r square would not act on sine square theta. So, it is only on the f of r. So, the second differential is only dou by dou theta. So, which would act only on the sine square theta. So, if you now look at these two, so what would happen is basically you have got sine theta by r square dou by dou theta 1 by sine theta, and then dou by dou theta sine square theta. Okay. So, that would actually give you sine theta by r square dou by dou theta, and you have got 2 sine theta cos theta by sine theta. So, then you would actually rule out these, and the dou by dou theta of cos theta, that would actually give you sine theta by r square, and this will give you minus 2 sine theta. So, it will actually give you minus 2 sine square theta by r square. So, sine square is then taken as a common. So, minus 2 by r square will come. So, minus 2 by r square has come here. So, which means that we have now a simpler form of the e square operator. So, the e square operator with the theta differential is here, and e square operator without the theta differential is here, and we were able to do this because our solution has a special form, namely of this form. Okay, that is, we are seeking a solution which is actually in two parts, and that is the reason why we are able to make this simplification. So, we now see that okay, we have a simpler situation of only differentiation with respect to r, and what kind of a solution we can seek for f of r. So, we propose that we seek a solution of f of r as a possibly a polynomial. So, r raised to the power of n, and see what values of n would help satisfy the governing equation. Okay, so, the governing equation is here. Okay, so, what kind of a values of n would satisfy? So, we go ahead and substitute that f of r here as r raised to the power of n. So, when you act first time, so you have basically dou square. So, when you act first time, you have dou square by dou r square r raised to the power of n, that would basically give you n into n minus 1 into r raised to the power of n minus 2, and then the second equation is nothing but 2 raised to the power of 2 into r raised to the power of n by r square. So, you basically arrive at this. Okay. So, that is n into n minus 1 minus 2, that is coming here. Okay. Now, when you act the same thing further for the second differential on this function, then you would actually see that you got one more set of quantities that are involving n, and then we knock off the r because we want to see for what values of n this is satisfied. So, if this is satisfied, then we got n available. Okay, those n's can be used to then expand the r raised to the power of n, and then we have got the solution. So, we multiply and check the functional form. So, we have got a polynomial form, and luckily for us this polynomial can be factorized, and that factors actually look like this. So, straightforward from these factors you can already see that the solutions are for n is equal to minus 1, then plus 1, plus 2 and plus 4. So, we can see that the solutions are readily available, and we can note that the functional form that we have r raised to the power of n can take any of these n's, which any of these values, which means that a combination of those should also work as a solution. So, that is what we do. So, we take a combination of all those forms. So, the n is equal to minus 1 is given the d term, the n is equal to plus 1 is giving the c term, and so on. So, a, b, c, d are numbers or quantities which should actually be multiplied, and then this summation actually is a possible solution. So, this is basically a possible solution. Okay. Now, it is only a possible solution, but we need to ensure that it actually satisfies the boundary condition, and we already have the boundary condition requirement here, that is in the limit of far field velocity you must have this particular equation that has to be satisfied. So, which means that when if you want to use f of r here, then it means that if you compare with this f of r in the limit of r tends to infinity should give you r square u by 2, and which means that 1 by r square f of r should give you u by 2. So, we now have a constraint on the f of r. Now, if you look at f of r by r square, then you would see that it would be a r square plus b plus c by r plus d by r cube, and now it in the limit of infinity you would see that these three will not give a problem because c and d will vanish. So, these will drop, these will drop, but this will blow up. So, which means that the only way we can actually have a meaningful solution is if a is 0. Okay. So, because of this condition we say that a is 0. So, that removes the problem for us, and b straight away we can see that f of r by r square should be taking a value of u by 2. So, b must be u by 2. So, we have got two of the constants determined in this manner. Okay. And now we see that when you substitute a and b values, so your possible solution form is now simplified, okay, like this. Now, we now have boundary conditions also for velocity on the surface of the sphere, and that actually will also be useful. So, we have seen these boundary conditions already, and this actually gives you, when you substitute, the two equations, and these two boundary conditions solved together they give the values of c and d, which are basically the integration constants or solutions of this particular equation that we have written. So, which we do it. So, you can do it by multiplying the second equation with r and subtracting and then so on. So, if you do that, then you arrive at the values of c and d. Okay. So, please do that so that you are getting these expressions the same way, and you will also when spend time on these expressions, and then you can also commit them to your memory, and that will be easier to remember the final form later on. Okay. So, now we have got all the four values determined. So, we have got the solution available. So, solution is this. Okay. So, solution is available to us, and the psi, the stream function is f of r into sin square theta. F of r is already available to us. So, we now have the entire psi form that is available here. Okay. Okay. Now, we already know that contours of stream function show how the flow takes place. Okay. So, what we have done here is a small one line MATLAB mathematical script to show you. So, you can see that we have actually seen this function, okay, that is nothing but the f of r, and then we are actually converting the coordinate system from the polar to the xy here, and then plotting them in a range, and you can immediately see that the contours look like how we have imagined. So, to just show you clearly, the sphere is of radius 1 because we have taken the value of u to be 1. So, this is the sphere, and we can see that the velocity should look like that. Okay, this is how we have already imagined how it should be moving. So, it should go around the sphere, and far away it should have the unidirectional velocity. So, you can already see that far away the velocity is unidirectional. So, this is how we can actually see that the solution we have obtained actually makes sense. Okay. And once it is available, so we basically now have the solution. So, we now can get this is in the form of psi. So, we can see then how the flow field is in Vr and V theta. So, that we would do now. The psi is available, okay, and so then we use the definition of Vr and V theta here, and then substitute this psi solution we have got, and substitute that into these expressions, and then we are able to get the components straight away. So, it is a simple differentiation that we are doing, nothing and there is no step in between to wonder at all. So, substituting the expressions for psi, you get Vr and V theta straightforward. So, we now have basically the velocity components that are available. So, this is basically the analytical solution, okay, exact analytical solution for the Stokes equation for the limiting case of creeping flow. Okay. So, for creeping flow over a sphere. So, you can see that the number of steps that are taken to arrive at the velocity components is way more than what it had taken for problems in rectangular coordinate system. So, which is also the reason why we must try and reduce the dimensionality of our problems to see whether some estimates can be made for rectangular coordinate system already, and in case the situation does not allow, then we can then go ahead and make it a simpler problem in coordinate systems like cylindrical or spherical as the requirement makes us do. Now, we have achieved up to here. So, analytical solution is available. So, technically the problem is over, but we now want to take this a little bit further up because of a particular metallurgical application that we normally are familiar. So, what we do is that we will use these flow fields to arrive at the pressure and shear stress distributions. So, both tau and sigma, that is basically the r theta and r r, and here pressure. So, we want to look at these quantities also, and how do we get these? This is basically via the linear constitutive equation, namely the Newton's law, which is actually connecting the shear stress and the velocity gradients. So, we will use and get those things, and then from there we will get the drag terms, and then from there we will get the Stokes law, and finally the terminal velocity concept, which is very useful in many of the metallurgical problems. So, the solution is already available to us, and the pressure and the stresses are then displayed here. So, we can see that the pressure is actually in this direction, and if you want to look at the RR, then that would be in the opposite direction. Okay. So, because of the convention that pressure is in the direction of compression, and therefore, we have got those things like that. So, we want to determine these, okay, what are these expressions, okay, and once we have them, then we can look at what would be the components of forces that are acting on the sphere in the z direction, and then look at the summation, etc. Okay. So, for that what we need to do is go one step back and look at the Navier-Stokes equation, substitute the velocities and get the pressure distributions. If you have noticed in the previous session, we have already done that to see how the pressure variation will come once we have the velocity components available. So, we are going to do that here also. So, the velocity components are available. So, then we substitute that into the Navier-Stokes equation, but keeping the pressure variations intact, so that we can get some functional form for P. So, we do that, we substitute and see that we get a condition which we need to integrate to get the P. So, we got the condition for pressure variation in the radial direction, given that the radial velocity component is so and so. So, we have got one term there, and similarly we substitute the theta component here, and we substitute that also here, and we substitute the r component here, and we can then get the pressure variation in the theta direction. So, once these two are available, we can then see what kind of a pressure form would let us combine both. Okay. So, do try out by substituting the velocity components in this equation and arriving at the pressure variation as that is written here. So, that is a couple of steps of algebra, but quite straightforward. So, these are the two conditions, and from here we seek a form for the pressure. Okay. So, we want it to be a function of r and theta, and we only know the differentiation with respect to r and theta. So, by looking at them, we have to guess what kind of a form would allow us to get this, and this solution is then suggested as follows, and C1 is basically the integration constant. So, it is easy to see that once we have got the suggested form, when we differentiate, would you get those two variations, that you can verify. And the integration constant is determined by looking at the pressure variation as a function of distance. We already know that from static problems. So, rho g h as the hydrostatic head is already known to us. P naught is the reference pressure or the atmospheric pressure. You can take for all practical purposes P naught to be 0 and then solve the problem. That is not a problem at all. So, z direction, the distance is r cos theta, and we are using that here. So, which gives us basically the pressure form, a function of r and theta is available. So, similarly we can get the, this is done. So, similarly we now seek what would be the shear stress distributions. So, for that we again look at the connection between the stresses and the velocity gradients. So, that is available here for the spherical coordinate system, and the velocity components are there. So, we can substitute, and you have a 2 here. Why is there? Because we see that the stress is actually a symmetric tensor. So, when you have the same index, then you have see that the same term is being added. So, you can actually then substitute and get the sigma RR, and sigma RR is then available in this particular form. Okay, so, you now have pressure and sigma RR, which means that we have the normal pressures that are acting on the sphere, pressure and stress that are acting, and therefore, its vertical component can be taken. Similarly, the shear stress can also be looked at, and you can see that it is written in a symmetric manner using r theta, and you can see that these two terms are available, and you have the r component and the theta component of the velocities that are present. So, you can then substitute them and get what is the tau r theta. So, the functional form for tau r theta can also be obtained readily by plugging in. So, once you have the velocity components, then you can see that the pressures, the normal stresses as well as the shear stresses can all be obtained. Technically, now you have all the terms to write, for example, sigma is equal to what. So, you can write it in a matrix form because all the terms are now available, but we only are requiring the r theta and rr components for this particular problem. Okay, so, once we have, so which is there, then we have to see how to calculate the drag. Drag is nothing but basically the integration of stresses that are acting on a solid surface over the entire surface. So, we will get basically when you integrate stress with an area element, you get basically force. So, that sum of all those forces is basically the drag. So, that is what we are going to look at now. So, now we have already seen that the theta variation in this manner. So, if you look at how the normal stress has to be computed in the vertical direction, you could see that here the pressure would come straight away as minus p, and cos theta is 0. So, minus p it will come, and sigma is actually going to be plus sigma RR, and here actually it will be 0, and here it will be again minus direction. So, you could already see that this part is basically taking the stresses and giving a component which is in the component in the z direction. Okay. And now, this is the stress component that is acting in the z direction on an area element. That area element is given in this form. So, r d theta r sin theta d phi is the area element for a sphere of radius r. Okay. So, this is already available. When you integrate this alone over 0 to pi for theta and 0 to 2 pi for psi, then you already get the surface area of a sphere. So, we already know this from the high school geometry problems. So, we can then substitute this part, and we are going to integrate this entire term to get the force that is acting in the z direction because of pressure and the normal stress. Similarly, for the tangential, you can already see the components are actually sin theta. So, it is tangential, is normal. So, if this is cos theta, it will be sin theta here, and this is the area element. So, when we integrate these, you get the normal direction, what are the forces that are acting. So, the pressure and sigma RR are available. So, you substitute those and then the cos theta is taken, and then this is the area element, and integration is over the sphere. Okay. So, when you do the integration, which again is not very complicated, when you go through that, you see that the normal force in the z direction is given by this. So, you can already recognize immediately that this term is coming out with the volume into rho, that is mass, into g. So, you can already see that this is coming because of this fellow. Okay, so you can readily verify that when you take this term and then integrate over the entire volume, you can already get this, but the rest of them also will be giving you these quantities. So this actually is a buoyancy force because it is basically caused by the gravity, and this is called a form drag. Okay, and you can do the similar kind of integration for the tangential stresses to give you the normal force or vertical direction force. So r theta is available, so the r theta is tau r theta is substituted, and then this is the area element, and then when you integrate it over the sphere, then you get the Ft as 4 pi mu r into u. So this is actually called as a friction drag. So there are two components of drag that are acting on the sphere because of the flow that is happening around it, the form drag and the friction drag, and as you can see, the form drag is coming from the normal stresses, the friction drag is coming from the tangential stresses. So when you add these two, so what happens? Okay, so you got these two, when you add, that is when you get the Stokes law. So basically the normal and the tangential components of the forces in the z direction are available. So when you then add them up, it should actually match the weight of the solid in case the total forces cancel and the solid is actually falling down at a velocity u, which is the terminal velocity. Alternatively, the fluid is actually moving upwards in the direction and the solid is stationary. So it is only relative velocity that we are looking at. So when you put these two and substitute into this, then you can get this equation which tells you that, of course, this can be taken as delta rho. Okay. So which basically tells you that because of the density difference, the buoyancy is actually compensated by a force, and that force is actually going as 6 pi mu into r into u. Now this u is then called as the terminal velocity. So u is basically the terminal velocity. Okay, terminal velocity when this balance is happening. Okay, so if this balance does not happen, then of course you still are able to work with the fluid flow variations, but it is just that this flow pattern has not stabilized and you still have the body, solid body accelerating, etc. And this is also given a name, the Stokes law. So Stokes law is actually then valid only for creeping regime, which means that the Reynolds number has to be very small. Okay, so this is a validity range, and whenever we want to arrive at with the velocity of the solid that is falling in the liquid column, and if the solid is having a radius r and the liquid is having a viscosity mu, then we want to find out what is the u. Then when we use this formula, we have to ensure that calculating Reynolds number, it would give us a number that is very small. So that is only when the creeping flow regime is valid. So we have then finally arrived at the end of our concept map. We could see that we started off by looking at the stream function definition, the E square operator we have introduced, and we have seen that the Stokes equation is being used for our solution because we are actually in the creeping flow regime. And then from there we sought the solution of the stream function psi, and then that gave us the velocity components Vr and V theta, and then from there we got the tau r theta and then the sigma r, then we got the pressure, from there we have got the forces, and from there we got the balance with respect to the weight of the solid, and then we got the Stokes law, and the velocity at which the forces are balancing, we actually are calling it as a terminal velocity u infinity very often, or in our problem it is just u. So like this we are able to now cover the entire problem in the complete depth that we need, and in the sample problems in the course website you will have some numerical problems given where we are going to apply the Stokes law. So these are actually of very high importance in the extractive metallurgy problems. So to know how these equations came about and which analytical solutions made these possible is important, and I hope this session would have clarified the entire process of arriving at that.